Hi, good afternoon, everyone. Thank you, Mr. Chairman, for the introduction. I'm Aniello Falco, and I will present this work in simulation and fabrication of polarized organic photodiodes. I'll go through a quick outlook, which is I'll first give a background and motivation, because not necessarily everyone in the audience might know about the printed electronics and why we want to integrate it with grid polarizers. Then we'll show you how we decided to simulate bilayer wire grid polarizers with a multiphysics software. And we present the idea of a self-polarized organic photodiode. We simulate this overall structure with means of a drift diffusion model. And then at the end, we fabricate this device and we check it out and see if it really works or not and how bad or how good it works. And then I'll go to conclusions and outlook. So why printed electronics? Printed electronics is amazing. That's why printed electronics is because we could do in principle everything. Every material that could be put in solution can be deposited by printing, inkjet printing, spray deposition, slot dyeing, and other techniques, and could be engineered in order to have whatever properties we want to. Like for instance, here you can see a very nice work by the group of Professor Javi, where they do a fully printed transistor with an engineered insulator, with printed electrode with silver nanoparticles, and with printed carbon nanotubes. But that's not the only reason why we want to do that. It's also because using this kind of technologies and using the deposition techniques that we know, it is very easy to go up to scale and to go for large area electronics. What you see here is a roll-to-roll manufacturing facility, again from the same group. And it's pretty nice because it says that we can actually manufacture on a very large scale and to a very low cost. Why very low cost? Because the solution processing is at low temperature and in ambient conditions also in terms of pressure. So this would be very green, environmental friendly, and also to a very low cost. Furthermore, the intrinsic characteristics of organic electronics and printed electronics are that are flexible. Most of them are biocompatible, are lightweight, and customizable in color. This means that you can, now as the LG display would say, blacks, which are true blacks, that's something that you can obtain, or we can go for real biochips that are biocompatible and so it could be easily integrated into the human body. We thought that we could integrate organic electronics and light sensing organic electronics with light polarization sensing. Why light polarization? Because, for instance, you can find targets and isolate them, and as we've seen in today's plenary talk, where there are the militaries, there's lots of money, so that's a good, where there are the militaries, there's money, so it's very good to invest in there. It's also useful for medicine, like in this case for melanoma detection. It's good for astronomy. The polarized light of the stars has been used now for more than 6 decades, and in biology and chemistry. The target we were aiming to is to use, for instance, the polarization of light into so-called cross-polarization technique to detect the fluorescence. So now, cross-polarization technique means that we have a source of light, a first polarizer over there, then we have a fluorophore. So imagine that this light is horizontally polarized. The fluorophore will emit non-polarized light, will go through the other polarizer, and then in the end, we'll only be able to detect the vertically polarized light that has been emitted by the fluorophore. This system is in principle pretty simple. It is made by microfluidic chip, a light source, 2 linear polarizers, and a photodetector. The real problem is that we have to put all of it together. And put it all together can be complicated. Sometimes they literally use Scotch tape or super glue to do it. It's not a nice process to do, and we get lots of insertion losses, and we need external components. So we need to buy the polarizer somewhere. And we thought that since organic electronics is very versatile, we could try to integrate a grid polarizer and use it at the same time as a grid polarizer and as an electrode for our photodiodes. That's because grid polarizers are made with metals, and the metals such as aluminum, gold, or silver can be used in organic electronics. When I say grid polarizer, I mean an object which ideally is able to, it's a filter which is ideally able to give us only one component of the light, for instance, the X component. Which can be, this kind of filter can be approximated as a metamaterial which in one direction behaves as an insulator and on the other direction behaves as a perfect electrical conductor. And the good approximation and periodic approximation of this filter is given by this kind of structure. You have metallic grid lines which are spaced with a distance which is below the wavelength. In this way, on the Y direction, we're going to have a perfect metal, so you have enough space for an electrical current to insert, and in the other direction, the horizontal one, it will be broken, so you will not have enough space to have an electrical current. So this means that on the X direction, we're going to have the refraction of 2 normal insulators, while in the Y direction, we expect to have a reflection which is similar to a bare metal. So this plot here is the reflectivity of gold, aluminum, and silver, and so we'd expect something like that. I finish with just short remark on the structure we're really going to consider. Is not this very simple grid polarizer we see here, but it's this other structure over there. That's a bilayer grid polarizer. It's just imagine we have two of them, one over the other. It's not exactly like putting two of them together in series because they are at the distance which is below the wavelength, so there will be some interference. Actually, there is some Fabry-Perot resonance, but this structure is pretty efficient. It's like up to 2 orders of magnitude more efficient than a single layer grid polarizer. Plus, it's much easier to manufacture. As we will see later, the manufacturing of this structure is extremely straightforward. So we proceeded with the simulation with simple multiphysics software. We solved the Maxwell equations in that region. Do not be afraid of the too many plots. Just consider the top side. Top side is the extinction ratio. So it's the ratio of the transmitted TM field to the transmitted TE field. Yeah, exactly, yes. And you can see it for different metals, silver, aluminum, and gold, and with a sweep on the thickness of the metal. What we can see is that the thicker the metal, the better is the polarizer. And actually also looking at the spectrum, we can see a very nice shift towards the blue, which means that our metal is approximating much better the flat metal. So our approximation of the metal material makes much more sense if we have a thicker metal. The bottom panels represent the transmission spectra. So it's basically if you put together this information of the bottom layers, make the ratio, you obtain the top panels. So it's not important to look at that. Now we take this structure. We know it works because we did the simulations. We actually also fabricated. We discovered that after fabrication, the extinction ratio that we got for aluminum, which is the best one here, it's not even by far approaching this value there, and that's because of some non-ideality during the fabrication. We took in account that we remade the simulation, and we ended up to see that if you consider real structure, the extinction ratio of an aluminum structure with 45 nanometer thick lines will be very similar to the theoretical one of a 15 nanometers thick lines. So we took that in account, and we went on to the next stage. Next stage is the creation of a polarized organic photodetector. So first, we need to create the polarizer. How do we do that? We use a material which is called ormostamp, which it's imprintable, so it's a polymer. We just dispose a droplet of this polymer. We use a master stamp, which has some grid lines in it. And then we wait a bit of time and we expose it to UV light. The underneath polymer cross-links, so it becomes hard and replicates exactly the stamp that we used before. So we maybe pay 10,000 euros to get an E-beam stamp to the nanoscale, then we do not need to pay money anymore. We just do it almost for free. Once you remove the stamp, you have a negative replica, which in our case it's okay, since it's grid lines, so negative and positive is almost the same. We just need to evaporate aluminum. If you evaporate aluminum now, you will have an aluminum layer on top and an aluminum layer in the grooves, which is exactly our bilayer grid polarizer. That's why it's very easy, and it's better than a single layer grid polarizer. At this point, we have an aluminum layer that we could use as an electrode. In the 3D version here, you can see that it's not only evaporated in the middle where the lines were, but it goes also a bit out. In this way, we can use it as an electrode. We can deposit P.PSS, which is the material that we normally use to adapt the work function of the metals to have a higher work function. And we deposit the bucketer junction, so the semiconductor itself, and then we evaporate a calcium aluminum layer on top. And in the end, we have a complete photodiode, which is able to have the bottom electrode, which at the same time is an electrode, and a polarizer, simplifying a lot the structure. We decided then to simulate it with a drift diffusion model in Centaurus TCAD. That's what we considered. For the light, we used the most simple optical solver, but instead of giving it the normal light that we would give like a monochromatic light, we gave the light that we simulated in the previous step. So we simulated the light that would pass through the grid lines here, would get at this level here, and then it gets inside the photodiode. Simulating this, just using a normal optical generation like standard, we obtain some good results, but first I'll give you some more details on the model we considered. I will not read all of it, but in the end, it's pretty standard. We use an approach which is called the virtual semiconductor approach, because the bucketer junction is composed of two semiconducting material, a donor and acceptor. The idea is that you just put it all together, you average it, and you obtain the refracting index of these two materials. We consider some shallow and deep traps according to literature, and in the end, the results are the following. So here you see that, yes, it's my fault. Yes. So here you see the IV characteristics. The blue line, it's the dark So there is, in reverse, there's a very low current. Then we illuminate it with the TE mode, and we get the green one. Then you illuminate it with TM mode, and you get the red one. There is more than one order of magnitude between the two. So this means that this concept that we developed, at least on paper, it's working. Considering the external quantum efficiency, so spectrally resolved, we have something like that. Again, TM is much higher than the TE, and the shape, it's not the most beautiful Gaussian shape I've ever seen, but still, it's a good approximation of the normal spectrum of organic photodiodes with this material stack. And the result was very encouraging, so we thought we have everything. We know how to do a grid polarizer. We know how to spray deposit the photodetector onto a small area, because that's actually one of our core expertise. So why not fabricate in it? And that's what we got. So first we make the ormostam. First we got the ormostam sample. We evaporated aluminum, and here you can see a picture of the microscope with the polarizer in TE and TM mode. In the TE, we have a full refraction. In the TM mode, we have a window. So that's an optical window, and the light is able to pass through it. Then we spray deposit pilot PSS, nothing changes. The polarization capabilities are kept. And then again, we spray coat a thin layer of P30 PCBM, and the polarization capabilities are kept. And now we can see here a picture. I'm sorry for the bad quality, but I just took it with the cell phone, and I put the polarizer in front of it. But if you align the polarizer with the grid lines, you would have like a plain aluminum layer, basically. So the light does not pass, it's reflected back. While if you go on a TM mode with the polarizer in front of the camera, you can see that it opens up this clear optical window. And that's how it works. And that's why in the end we got IV curves which are relatively similar to the simulation, a bit worse, especially in terms of serial resistance, and the external quantum efficiency, which is again pretty good. The ratio is about 30-35 with respect to the TM. And with this, I basically conclude. So what we obtained was grid polarizer. We integrated them with photodetectors. What we want to do is to make better photodetectors, better grid polarizers, of course, and maybe integrate that also in OLEDs instead of only OPDs in order to have a complete vertical system. Thank you.